Hello. Today we are going to discuss cyclic permutation. Let us start with an example belonging example of permutation belonging to set having 7 elements 1, 2, 3, 4, 5, 6 and 7. So a permutation defined on this is like this one 1, 2, 3, 4, 5, 6, 7, 4, 7, 3, 5, 2, 1 and 6. Here we see that image of 1 is f image of 1 is 3, f image of 2 is 5, f image of 3 is 2 and so on. So we clearly see that image of 1 is 3, image of 3 is 2, image of 2 is 5 and image of 5 is 1 and image of 5 is 1. So image of 5 is 1 and other element having their own image, image of 4 is 4, under map image of 6 is 6 and image of 7 is 7. So this permutation can be written as this type only. Means we generally avoid to write single elements since they are cycles of length 1 and we may avoid to write these cycles. So a permutation can be written as a cycle, or it may be disjoint cycle. Say for example, image of 4 is 6 and image of 6 is 4. So this is image of 4 is 6 and image of 6 is 4. So I can also write this permutation as two disjoint cycles. Disjoint cycles means the cycle which does not have any common elements. So we can define cyclic permutation in mathematical notations as, suppose we have a set of n elements like this, and out of these n elements we find a permutation such that image of x1 is x2 and image of x2 is x3 and so image xr, means these are the r elements. Out of these n elements having images of x1 as x2 under map f and image of x2 is x3 and so on. So this we can write fx1 is equal to x2, fx2 is equal to x3 and so on. fxr minus 1 is equal to xr and f of xr is equal to x1, and all other elements having their own images. So we can say in general fxi is equal to xi plus 1, where I is equal to 1, 2, 3, 4 and r minus 1. And for xr, f of xr is x1 and all other elements other than these r elements we can find fxj is equal to xj, where j is not equal to 1, 2 and r. say is not equal to 1 to R, other than these R elements, image of n element is itself under the map F. So this is the cyclic representation of any permutation, or this may also contain X, S and XP, XP, these two elements or three elements, or may be of different cycles of different length, like this. So any permutation can be expressed as the cycle, or as a combination of disjoint cycles. This is the way to represent a permutation. Now, cycle of single length is known as identity permutation. Now, inverse of a cycle, say we have a cycle of F, and a cycle of F is equal to 1, 3, 5, 2, 5, 2. Image of 1 is 3, 3 is 5, 5 is 2, 2 is 1, 2 is 1. This is the cycle. And if you want to find out, cycle is nothing but a simple representation of a permutation with this cycle only. If we want to find out F inverse, then we simply write the elements in reverse order, that is 2, 5, 3, 1. So we can easily write F and F inverse. A permutation is represented like this. This permutation may also be written as 3, 5, 2, 1 is equal to 5, 2, 1, 3. Means I can keep the cyclic order intact and can write this permutation in different way. Means this representation I may represent a permutation in different ways, but keeping the cycle intact. So this is the way to express a permutation, cyclic representation of a permutation. Now we would like to find the order of a cyclic permutation. How can we find the order of a permutation? What is the order of a cyclic, or order of a cycle? Now, this is the list element where we can get the identity element after combining this. Say F is a permutation and image of X, Fx is say X1, say image of X1 is X2 and X2 is X3, X1 is X2 and so on. So what is the list element, list number where F multiplied by F, operated by F, again operated by F, F of F. When we get Fr such that Fx1 is equal to X1, then this R is known as the order of the cycle. That is order of the cycle. Means the list number when we get the image of the element as itself. Now, how can we find the order of a cycle? Let us take an example H. Let me to have a cycle like this: 1, 3, 2, 4, 6. This is the cycle. Means image of 1 is 3, image of 3 is 2, image of 4 is 1. So I can express this cycle as a permutation as 1, 2, 3, 4, and can write image of 1 is 3, image of 2 is 4, image of 2 is 4, image of 3 is 2, image of 4 is 1. This is the permutation, and therefore this permutation image of 1 is 3, 3 is 2, 2 is 4, and 4 is 1. So this is the representation of this is the cycle, and this is the permutation of related to this cycle. Now we want to find out the order of this cycle. How we can find f operation f means we have to operate this f with f. We will get 3, 4, 2, 1, and 1, 2, 3, 4, and 3, 4, 2, 1, and as we earlier seen that the operation to operate these two permutations we should write like this: 2, 1 here, and image of 3 is 2, image of 4 is 1, image of 2 is 4, image 1 is 3, and 1, 2, 3, 4, and 3, 4, 2, 1. So final result of this one is 1, 2, 3, and 4, and 2, 1, 4, 3. This can be find also with the help straightforward manner h. We use this image of f1 is 3 and image of 3 is 2. So I can write straightforward, I can write image of 1 as 2. Image of 1 is 3, image of 3 is 2 under the map f. So in squaring this I can write image of 1 as 2. And now image of 2 is 4 and image of 4 is 1. So image of 2 is 1. Image of 3 is 2 and image of 2 is 4. So image of 3 is 4 and image of 4 is 1 and image of 1 is 3. So image of 4 is 3. So I can find square in a straightforward manner this way that I explained. Now in order to find the f cube means I can write f square into f, or I can write f or f square, and this can be written as f from here I will find f 1, 2, 3 and 4. This is your f 3, 4, 2, 1. And what is f square? As you find here 1, 2, 3, 4, 2, 1, 4, 3, and the result, final result, we arrange and multiply all that, but I can straightforward write image of 1 is 2, image of 1, 2, 3 and 4, image of 1 is 2 and image of 2 is 4 here, so I can write 4. Image of 2 is 1 and image of 1 is 3, so I can write image of 2 is 3. Image of 3 is 4 and image of 4 is 1, so I can write 1. And image of 4 is 3 and image of 3 is 2, so I can write this. Thus we can find f cube, and yet we notice here that it is not an identity permutation. So again we try to find f4. f4 can be find out with this way, f or f cube or f cube or f square into f square. In any of these way we can find the f4. So let me to try f4 straightforward with the help of f square. So this is your f square. Now 1, 2, 3, 4. I can straightforward write the f4, f raised to the power 4 as image of 1 is 2 and 2 is 1, so image of 1 is 1. Image of 2 is 1 and image of 1 is 2, so 2. Image of 3 is 4 and image of 4 is 3, so it is 3. Image of 4 is 3 and image of 3 is 4, so it is 4. And we notice here that this is identity. Therefore, first time identity appears for F4, so order of this permutation is 4. And we notice here that this is equal to the length of the cycle, length of this cycle. If in place of this, if I have F is expressed as the combination of two disjoint cycle, then we can find the order of this F such that the LCM of, say, this have 3 elements, this cycle has 3 elements and this cycle has 4 elements. So order of this F is nothing but LCM of 3 and 4, and it is 12. I think it is 12. So order of this permutation will be 12 if I can express this permutation as the combination of two disjoint cycles. So in this way we can find the order of any permutation. In general, what we can do, say order of a cycle of length R is R. This we have to prove. Order of a cycle of length R is R. How can we prove this? Suppose we have a set x1, x2 and xn, means n elements. Out of these n elements, R elements have such that x1, image of x1 under F is x1 is x2 and x2 is x3 and xr. These are the R elements having such image, such a way that the x1 image, F(x1) image is x2 and x2 image of x2 under F is x3 and so on. X image of xr is x1 and all other remaining elements having their own images. So I can write Fx1 is equal to x2, Fx2 is equal to x3 and so on. Fxr minus 1 is equal to xr and xf of xr is equal to x1. So using these equations, I can write f square of x1 is equal to f square of x1 is equal to f of fx1, and this I can write at what is fx1? Fx1 is equal to x2, so this is x2 and this is your x3. Again, f cube x1 is equal to f of f square x1, f square x1. As we find this is x3, so this is your fx3 and this is equal to x4, and similar way fr minus 1 of x1 is equal to fr minus 1, this is your xr, this is your xr, and fr of x1 is f of xr, and we know that fxr is nothing but x1. So first time this image of x1 under the operator of f gives us the same element. In similar fashion, we can find x2 image of f x2 image is fr x2 it will be x2 and fr x3 is equal to x3 and so on. Fr xr is equal to xr. Thus, and all remaining elements have their own images. So, say k is not equal to 1 to r, means k does not belongs to this set xr, this set, and I can write fr of xk is equal to xk, since fxk is equal to xk, so rth operators will give us the same element. So in general we can say for this set, if we have a cycle of length r, then order of this cycle will be r. This is true. Now, what is transposition? We prove some more results. A transposition is nothing but a cycle of length 2. Say, we have a cycle of length 2, say 1, 2. It is a cycle of length 2, it is known as transposition, and any cycle, let's say 1, 2, 3, 4 is a cycle, simple cycle. So this can be broken, and this cycle can be broken in terms of transposition as 1, 4, 1, 3, 1, 2 and this. So this cycle can be broken into transposition in this way, and transposition are nothing but cycles of length 2. Tomorrow we will see some more illustrations for these transpositions and related to the permutations. Thank you to all.